All right, let's dive into one of the most mind-blowing and maybe even terrifying ideas in all of physics, the many worlds interpretation. The basic idea? That our entire universe, everything we know, might be just one single branch on an infinitely branching tree of realities. So just try to wrap your head around this for a second. What if every single time a quantum particle has to make a choice, the universe itself splits in two, with each possible outcome playing out in its own very real parallel world? And no, this isn't just a fun idea from a science fiction movie. It's a serious proposal from top-tier physicists trying to solve one of the biggest puzzles in science. So you might be asking, why on earth would anyone propose something that sounds so completely wild? Well, it's because physics was kind of backed into a corner by a really deep and frustrating contradiction at the very heart of quantum mechanics. It's called the measurement problem. And here is the core of that problem. On one hand, you have the math. The beautiful, powerful Schrödinger equation tells us that particles live in this weird, fuzzy state of possibility called a superposition. A particle isn't just here or there. It's kind of in both places at once. But then there's us. The moment we look, the moment we take a measurement, bam, all that fuzziness is gone. We only ever see one definite outcome. The particle is here, the cat is alive, the two sides just don't seem to line up. For decades, the standard fix for this was to basically just slap a patch on it. They invented a rule called wave function collapse. It basically says, yeah, the math describes all these possibilities, but when you look, all but one of them just disappear. Poof, gone. But for a lot of physicists, this felt like a total cheat. It was an arbitrary rule that didn't explain how that happens or why. It was just a way of saying, it works, don't ask questions. And that's where a young PhD student named Hugh Everett III comes in. Back in 1957, he looked at this whole mess and asked a stunningly simple, yet completely revolutionary question. What if the wave function never collapses? Everett's crazy insight was that we've been thinking about this all wrong. The quantum rules don't just apply to little particles, they apply to everything, including us. So when you measure that particle, you don't force it to make a choice. Instead, you become part of the system. You get pulled into the superposition. And then the entire universe branches. In one reality, one version of you sees the particle spin up. And in another, totally separate reality, a perfect copy of you sees it spin down. Both are equally real. Okay, but wait, if this is happening all the time, why don't we feel it? Why don't we feel ourselves splitting into countless versions? The modern answer is a fascinating process called decoherence. The instant a split occurs, the new branches interact with their environment and almost instantly, they become completely isolated from each other. They can no longer communicate or interfere. So from the point of view of each version of you, it just looks like a single normal outcome happened. Now let's fast forward to today. Physicist John Carroll is one of the most vocal and persuasive defenders of many worlds. And his big claim is that it's not some complicated, bloated theory. Actually, he says it's the absolute simplest way to think about quantum mechanics. He says you can build the entire many worlds theory on just two and only two fundamental principles. And here they are. First, there's a thing called a quantum state that perfectly describes the universe. And second, that state always, without exception, evolves according to the Schrödinger equation. That's it. And the crucial part here is that both of these ideas are rock solid. They've been confirmed by pretty much every quantum experiment ever done. So this is Carroll's mic drop moment. The multiverse, the many worlds, they aren't some extra feature you have to add on. They are the unavoidable logical consequence of just taking those two simple, experimentally proven rules and applying them everywhere without adding any special exceptions, like that collapse patch. Now, of course, the idea of an infinite number of yous running around in parallel universes gets some pretty serious pushback. Carroll says most of these critiques are what he calls the wrong objections. They're based on common misunderstandings of what the theory actually says. This really gets to the heart of the simplicity argument. Look, many worlds has one simple rule. Everything evolves according to the math. The other theories? They all have to add extra stuff. Copenhagen adds the collapse postulate. Objective collapse theories have to actually change the math. Bohmian mechanics adds whole new invisible particles. So yeah, many worlds has a lot of worlds, but it has the fewest laws. And for physicists, that's incredibly appealing. But what about the biggest complaint of all? It's not science if we can't test it, right? We can't go visit these other worlds. But Carroll's answer is that you test a theory by testing its foundations.
And the foundations of many worlds, the Schrödinger equation, are some of the most rigorously tested ideas in human history. In fact, it's the rival theories that try to change the equation that actually make different predictions. And every time we've looked for those differences, we've come up empty.
So it all boils down to this fundamental trade-off. It's a question about Occam's razor. Many worlds gives you stunningly simple physical laws, but the price you pay is, well, an infinitely branching reality. The whole debate really comes down to what you think is more important, simplicity in your laws or simplicity in the world those laws describe. Now, this is not to say the theory is perfect. Carroll is very upfront about what he calls the real objections. These aren't just philosophical debates, they are deep, technical problems that physicists are still trying to solve right now. And you can see the difference here. The real problems are much more technical. The absolute biggest one is about probability. If every single outcome happens in some branch of the universe, what does it even mean to say there's a 50% chance of something happening? Where do the probabilities we measure in experiments even come from? Figuring this out, what they call deriving the Born rule, is a massive area of research. One of the leading ideas for a solution is called self-locating uncertainty. It's a bit of a mind bender, but the basic idea is this. Right after a split, but before you've seen the outcome, there are now two yous. You just don't know which one you are yet. So probability isn't about what will happen. Both things will happen. It's about how certain you should be that you've landed in one particular branch versus the other. It's a really smart idea, but it's crucial to know this is far from a done deal. Other physicists have raised some very sharp critiques, saying this doesn't really solve the problem, it just rephrases it. This is a very active, ongoing scientific debate. So after all of that, parallel universes, wave functions, decoherence, you might be sitting there thinking, okay, but why should I care? Why does this incredibly abstract debate matter at all? Well, it turns out the stakes are just enormous. Getting rid of that messy collapse gives physicists a much cleaner, more consistent starting point for tackling the biggest unsolved problems in science. It makes it easier to think about unifying quantum mechanics and gravity. It offers new ways to think about why time seems to flow forward. It essentially removes this weird human-centric measurement idea from our fundamental laws, which could be a huge step toward a final, complete theory of everyday physics. So that leaves us with the final, ultimate question. The many worlds theory forces us to make a choice. Would you rather have a simple, elegant set of physical laws, even if it means accepting that we live in just one tiny sliver of an unimaginably vast and complex multiverse? The answer you give isn't just about physics. It's about what you demand from reality itself.